Morning to all of you. If you remember in the last lecture we have discussed that convex sets, right? And convex set, what was the convex set that you have done with the graphically, right? The graphical way was that you draw the region of S, and then if you take any 2 points in the region S, if that line joining will belong to your S, then you say that your convex set. Otherwise, convex set we have done mathematically also, that if I take two points from the set S, if I write the CLC of A1 x1 plus A2 x2, that will also belong to S, where the condition that your A1 plus A2 should be 1 and that A1 and A2 should be greater than equal to 0. So we have discussed the set of feasible solution, set of optimal solution, convex or closed half spaces, open half spaces, will all forms your convex set. So next we are going to do a proof, that is you can say a theorem or one, that you are saying that the intersection of finite number of convex sets is convex. So this we have to prove. That means whatever we take the intersection, that will be your convex set. So we are taking, because we have to take finite number of intersection. So let I am taking S1, S2, Sn, B, N convex sets, and S1 intersection S2 intersection Sn be the intersection of n convex sets, right? I'm denoting this intersection by the set S. S is equal to S1 intersection. So what actually we have to prove? We have to prove that the set S is convex. To prove the convex, we take 2 points from the set x1 and x2, right? We take 2 points x1 and x2 from the set S, and we will show that the CLC also A1 x1 plus A2 x2 will also belongs to your S, and your A1 and A2 both will make as 1, and your A1 and A2 greater than equal to 0. So if you write, some books write CLC like this, A1 x1 plus A2 x2, because you take the sum as A1 plus A2 equal to 1, and then your A2 will become 1 minus A1. So some books write like this, that it is AX1 plus 1 minus AX2. When you have a condition A1, A2 greater than equal to 0, then it will give you 0. Your A should lie between 1 and 1. So this is the different ways that some books write, because you have to write the CLC of 2 points. So in this way we will start. So now we have to take 2 points from S. So we are taking 2 points x1 and belonging to your S, which implies that x1 and x2 will belongs to my intersection, because S is denoting nothing, but S is my intersection of Sn. Now we know, if I have something which is belonging to intersection, that means this is the common part where it is belonging, which implies कि मेरे x1 x2 सारे sets में भी present होंगे. That means x1 and x2 will be present in S1, x1 and x2 is present in S2, and x1 x2 will be present in Sn. Now we have given that these S1, S2, Sn are convex sets. So we will apply the definition of Sn. Since S1, S2 and Sn are my convex sets, which implies that if I take any 2 points from the set S, right, their CLC will belong to the set S, because the set is convex. So which implies, since these 2 points are belonging to S1, S2, Sn, which implies that the CLC of these 2 points will also belong to S1. The CLC of these 2 points will also belong to S2, and similar way it will belong to Sn, right? Now because the same condition, because SIs are convex set. Now since these are convex sets, and the CLC is belonging to S1, S2, Sn, and obviously since it is a CLC, so it has a condition that A1 and A2 is 1 and A1 and A2 are greater than equal to 0. Now, since this is belonging to S1, S2, Sn, which implies that A1 x1 plus A2 x2 will belong to their intersection as well. S1 intersection S2 intersection Sn, which implies that A1 x1 plus A2 x2 will also belong to the set S. Now you have taken 2 points from the set S and you have shown that A1 x1 plus A2 x2 will also belong to your set S, which implies that means your set S is convex, and S was nothing but that was the intersection of S1, S2 and Sn, right? So that means you have proved that the set S is convex. So you can notice over here, right? Like we have done the convex, we have done the graphical method, right? So in graphical method, if you notice, when we plot the constraints, that means that we have closed half spaces. अगर आपको याद होगा तो हमारे कंस्ट्रेंट किस तरीके के होते थे, या तो लेस देन, ग्रेटर देन, दैट मींस दिस फॉर्म्स अ क्लोज्ड हाफ स्पेसेस. व्हेन वी फाइंड द फिजिबल रीजन, राइट, जो आपका फिजिबल रीजन होता था, दैट यू सेटिस्फाई, यू टेक ऑल दोस point, all those area, all that area which satisfy your constraint. That means जो आप physical region लेके चलते थे, that you take as the intersection of closed half spaces. तो अगर आप ये closed half spaces की intersection लेके चलते थे, that means that will be your convex set. इसीलिए वो आपका convex set होता था, क्योंकि intersection of finite number of convex set is intersection of finite number of convex set is convex set, right? That's why it we take like this. Like you already done in your linear algebra, that you take H1 and H2 two groups, their intersection is also subgroup, but their union may not be. The same remark is over here, right? That the union of convex set may or may not be convex, right? So, you know, when we want to prove something, then we give the general proof. But when we want to disprove something, that means it does not hold. So, we always give an example. So, we can consider an example. You can consider S1, all those points that X1 is of type X1, X2. That means it is belonging, this X is belonging to your R2 plane. And it is satisfying that property that your 2x1 plus 3x2 is less than equal to 6, and you can take x1 and x2 greater than equal to 0 to remain in the first quadrant. Otherwise, if you will not remain, take this inequality, that means greater than equal to 0, still it is a closed half space and it will be your convex set. So S2, again you can take any 2 points x1 and x2, that you take 3x1 plus 2x2 less than equal to 6, and you take x1 and x2 greater than equal to 0, right? You can notice there, this is a convex set. Both of these are convex sets, right? Either you can prove it graphically or you can prove it mathematically. If you want to prove it graphically, how you will proceed? That you take 2 points to draw the constraints. So from the first S1, if I'm drawing the region of S1, so this is my taking X1 and this I'm taking X2. So if I'm plotting this, so this you can notice the point here, I'll get 3, 0 and point, and the other point I'll get as 0, 2, right? So this is my point. So if I join them by a line, so if you notice that this is, if you notice, this is my S1, and if you take any 2 points over here, you join them by a line, it will remain anywhere, you can take, you can join them by a line, right? Then this set is convex, that it clearly indicate S1 is convex. So if you want to plot your S2 is, if you take the points, it will give you 2, 0, right? And it will give you the point 0, 3, right? So if you join them by a line, so it will be a line like this, right? And you can notice over here this thing, that if you take here, like this is the visible region for your S2, right? And this set is also convex. You can take any 2 points anywhere and it will remain in that. But now we are taking the union. I am saying S1 union S2. That means all those x, and it is a 2 tuple set obviously, right? Where 2x1 plus 3x2 is less than equal to 6, or it can be your 3x1 plus 2x2 less than equal to 6. So if you shade this region, you can notice there. So this is your common region for your S1 union S2, right? That means now we are, if you take 1 point over here, and if you are taking second point over here, if I am joining them by a line, right? So this you can see the points lying over here is not coming in S. That means it is not in the union. That means it clearly says that it is not convex set. So you have given example, counter example, that you have two sets which are convex, their union is not convex, right? So this either you can prove mathematically. If you want to prove it like mathematically, then you have to go by the definition that you are taking x1 and x2. This is a two tuple set, and you are taking 2x1 plus 3x2 less than equal to 6, and you are taking x1 and x2 greater than equal to 0. If you want to prove this is your convex set, right, and you have to prove it mathematically, right? So how you can start? This is the simple funda, that you take 2 points x1 and x2 that you are belonging to your S1, right? And notice over here x1 and x, throughout my videos, capital X I am taking the point, and small x I am taking the points which is the coordinate which is deciding. So if my x1 and x2 are belonging to x2, what will be the type of x1? Obviously x1 and x2 this will be of R2 plane. So it is x1 comma x2. Because it is coming from the first number, so I am writing here x1 and this. And this is also of type x1 and x2 because it is coming from the second number, so I can write like this, right? I have taken 2 points from S1 and I have to prove S1 is convex. That means what do you have to prove? Prove is that you have to take the CLC of these 2 points, A1 and A2 and X2. That should also belong to S1. And if you notice, you have to use your vector addition and multiplication. A1, X1 is nothing but what is your X1? X1 is your X11 and this is X21. And A2, X2 is nothing but X12 and X22, right? So if you do the vector addition and multiplication, A1 will be multiplied by this and this, and A2 will be multiplied by this and this. And if you will use the addition, so you will come A1 X11 plus A2 X12. The first coordinate will be added in the first and the second coordinate will be added in the second. So if you have this thing, that means it is of the type number. I can say this is y1 and y2. So this you are taking 1 point, जो आपका CLC है, that means CLC आपका भी 2 coordinate that will also belong to your R2, and you have to prove that this y should belong to your this. You have to prove this, that you have to prove that y should also belong to S1. If I have to prove y belongs to S1, that means what I have to show? I have to use this property कि वो y x में S1 में मेरा तभी जाएगा if it is satisfied 2y1 plus 3y2 that should be less than equal to 6. If I'll show this thing that y1 and y2, y1 plus 3y2 is less than equal to 6, that means my y will belong to your S. So you can start that you take your 2y1 plus 3y2. Now your y1 is nothing but this value. So if you take, this is 2a11 x11 plus a2 x12 plus 3 y2 is this. This is your a1 x21 plus a2 x22. So if you do, this will be your 2a1 x11 plus 2a2 x12 plus 3a1 x21 plus 3a2 x22. Right? So now you can club these terms. This is your 2a1 and this you can take a1 as common. So it will be 2a1. sorry, a1 you are taking common. So this is 2x11 plus 3x21. And this, if you take a2 common, this is 2a2, 2x21 plus 3x22, right? So this I'll get, this is nothing but this is 2x2, x, I have taken common x12, and this is x22. So now you can notice over there, you are saying that x1 and x2 are belonging to my s1. x1 आपका nature किस तरह का, इस तरीके का, and x2 is nature of this. That means if this x1 is belonging to my s1, it is satisfying the property that 2x11 plus 3x21 that is less than equal to 6. Similarly, if I have x2 is belonging to my s1, that means 2x12 plus 3x22 is also my less than equal to 6. So you can notice over this thing, this quantity we have here. So it is less than a1 into 6 plus I have a2, this is less than equal to 6. So which is equal to 6, I can take common a1 plus a2, because this is a CLC, the sum of a1 plus a2 is 1. So we have over here 6, which implies that 2y1 plus 3y2 is belonging to my, is less than equal to 6, which implies my point, which is of type y1 and y2, is also belonging to S. Now what was my y? Y was nothing but that was my CLC, that a1 plus a1 x1 plus a2 x2, that also will belong to S, which implies your S is convex, right? Here S is, I am taking S1 set. So this way is the mathematical way to prove any set is a convex set, right? Next, we are going to do the fundamental theorem of LPP. This is very important theorem that we have used actually in graphical method. Since it has a name, so the statement can also become, if you are preparing for exam, but the statement is, it is saying that if LPP has an optimal solution, then it lies on, it lies, then it lies at least on one vertex of feasible region of considered LPP. The proof is for this. Before starting this theorem, I need to tell this we are doing for the maximization case, right? That the LPP is of like this, maximize Cx subject to Ax, you have constraint either can less, equal or greater, and it should be equal to B and your x is greater than equal to 0. I'm doing it for the maximization. The same I'll tell you for the minimization. There is just one change in that. So just starting this, I just want to tell you some the remark that you can notice. If I have any numbers, if I am taking, suppose this is my number 2, 3, 7, I am taking any number, right? And if I find the minimum of these two numbers, this will be 2. And if I find the maximum of these number, that will be 2, 3, 7. This will be my 7. So I have these three numbers, right? If I want to write the CLC of these three numbers, CLC of 2, 3, 7, what it will be? That is A1 into X1, that is my 2, A2 into X2, that is my 3, and A3 is nothing. A3 into X3 is 7. So, and obviously A1 and A2, A1 plus A2 plus A3, that is equal to 1, and all AIs are greater than equal to 0. So this is the CLC of this. So you can notice over this, this is A1 into 2 plus A2 into 3 plus A3 into 7. This CLC will always be greater than equal to the minimum of the numbers, the which is given to me 2, 3, 7. You can notice over here this thing and the same. अगर आप a1 को क्या रखोगे, now you know minimum is your 2. Now if you can also take that my a1 is 0 and a2 is 0 and a3 is 1, so you get the value as CLC value will be 7, which will be always greater than equal to 2, minimum of 2, 3, 7. It will hold equality when it will give, I'll take a1 as 1, a2 equal to 0 and a3 equal to 0. At that means it will have equal. That means CLC की वैल्यू या तो 2 से बड़ी होगी, 2 से ही बड़ी होगी, एंड द सेम थिंग यू कैन नोटिस ओवर दैट कि इसकी वैल्यू आपकी 237 से लेस होगी हमेशा ही. दैट मीन्स जिस भी नंबर का आप सीएलसी निकाल रहे हो, यू कैन नोटिस जितने भी नंबर्स का आप सीएलसी निकाल रहे हो, सीएलसी की वैल्यू हमेशा ही मिनिमम वैल्यू से बड़ी होगी, राइट? And it will be always less than the maximum of the same numbers. You can put any value of a1, a2 because you have to take your ai's are greater than equal to 0 and the sums should be 1. So if ai's will be fractions, so obviously when you will multiply with the fraction, it will remain in the numbers 2, 3, 7. So this criteria, this remark that we will use कि जो भी आपका CLC होगा वो हमेशा उन्हीं नंबर्स के मिनिमम से या तो बड़ा होगा और उन्हीं नंबर्स के मिनिमम से जिसका आप सीएलसी ले रहे हो उनसे दैट विल बी लेस देन इक्वल टू 237. सो वी विल नाउ गोइंग टू स्टार्ट इट्स प्रूफ बिकॉज वी हैव टू टेक द फिजिबल रीजन. सो व्हाट वी आर टेकिंग, आई एम टेकिंग लेट x1 x2 xn be n vertices of feasible region of LPP, right? And X star is the optimal solution. Of considered LPP. जो भी हमने LPP लिया, that means I have taken the LPP. This maximize CX. Now the case one here can be, the case one is that the simplest case if X star is vertex. अब आपको proof basically क्या करना है कि ये जो X star है वो आपको क्या कह रहे हो that your LPP has an optimal solution and it lies on vertex. That means जो भी आपको prove करना है that X star you have to prove that X star is a vertex. So the case one is the simplest, that X star is vertex, then we have nothing to prove. Then it is given, it we have taken कि X star जो है मेरी vertex है और vertex पे मेरा solution exist कर रहा है, right? The case two, if X star is not the vertex of feasible region. You know, अगर मेरा X star vertex नहीं है, we have done, तो इसका vertex नहीं है तो मतलब वो extreme point नहीं है. Extreme point को मैं सिर्फ CLC में नहीं लिख सकती, but any other point I can write as a CLC of other points. अगर मेरा X star vertex नहीं है, then I can write X star as the linear CLC of these. That means your AIs are greater than equal to 0 and AIs are sum they are making as 1, right? I can write it as the CLC because we have to take the objective function. Objective function में मेरा क्या है? C. So I can multiply C on both the sides. So if I'll take this A1 can be common, the CA1 X1 and this is just a scalar. I can take A outside. So this is CX1, this is AN, CXN. Now you can notice over here this thing. आप CLC कैसे लिखते हो? X1, X2, XN. अब ये CLC किसका है? Now this A1, A2, AN. Again you have this thing that AIs are making greater than equal to 0 and AIs are sum is 1. So this is nothing but this is the CLC of the points CX1, CX2 and CXN. Now we have done the theorem. अगर जैसे मैंने लिखना होता मतलब it just for your clarification I can write like this A1 Y1 A2 Y2 and an yn. If you are getting and we are not getting to understand what is how I am writing, so this is nothing, this is just representing the CLC of y1, y2 and yn. But what is my y1? That is my cx1. What is y2? That is cx2. What is yn? cxn. So you can also understand in this way that this is represented is nothing but this is the CLC of cx1, cx2, cxn. Now we have done this कि जो भी मेरा CLC होगा हमेशा वो मैक्सिमम से छोटा होगा और मेरा मैक्स वो क्या होगा मैक्सिमम से मिनिमम क्वांटिटी से बड़ा होगा. So that means if I am considering the maximum case, that will be less than equal to the maximum of cx1, cx2 and cxn. So I am taking this as some particular value. मैंने बोल दिया that this is cxp, where I am taking the maximum value. cxp is nothing but the maximum of cx1, cxn, right? So now you got that your cx star is less than equal to cxp. This is your first equation. Now if you notice, if you remember, हमने x star क्या लिया था? We have taken x star is the optimal solution of considered LPP. My LPP was my maximization. इसका मतलब अगर x star मेरा optimal solution है, तो optimal वो कब होगा? जब मुझे x star पे maximum value मिलेगी. Now further, x star is the optimal solution considered LPP, and my considered LPP is of maximization case, right? This is my maximization case. So which implies कि मेरे जितने भी मैं वर्टेक्स पुट करूं हमेशा ही मुझे cx star पे I'll get the maximum value. Either it will be greater than the maximum from all the values. जितने भी पॉइंट्स पे मैं वैल्यू निकालूं मेरी हमेशा उनके मैक्सिमम से या तो बड़ी होगी या मैक्सिमम से के इक्वल होगी. विच इम्प्लाइज ये आपने लिया क्या था दैट यू हैव टेकन cxp. So from the 1 you are saying cx star is less than equal to 1. From the 2 you are saying it is greater. So what it indicates? cx star is equal to cxp. C can be cancelled, which implies that x star is the vertex of feasible region of LPP, राइट? तो मतलब x स्टार आपने शो क्या कर दिया, वो कुछ नहीं है और ये p भी कहीं से ही आएगा, इन्हीं x1, x2, xn में से ही कोई पॉइंट होगा, राइट? सो x स्टार इज द वर्टेक्स ऑफ द फिजिबल रीजन ऑफ LPP. द सेम अगर आपको केस आता है मिनिमाइजेशन का, हेयर योर इनइक्वालिटी विल बी चेंज, ओनली व्हाट विल बी चेंज, जहां पे आपने ये लेस देन इक्वल टू मैक्स करा देन इट विल बी ग्रेटर देन इक्वल टू मिनिमम ऑफ cx1. अगर वो आपका ऑप्टिमल सोल्यूशन है तो यहाँ पे भी ये चेंज होएगा दैट इट विल बी लेस देन इक्वल टू मिनिमम ऑफ cx1 and cxn. So ultimately you will get the solution at the vertex. So you can remember that we have done when graphical solution हमने हमेशा ही vertex पे निकाला. That's why this is the reason, because the optimal solution if it exists it will be on the vertex, right? So now since we have done this, so just one point that I will end here. So one, because we have done all the things, so one we are doing polyhedral, sometimes we call polyhedron. You call a set a polyhedral or polyhedron a set which is formed by intersection of finite closed half spaces is a polyhedron or polyhedron. So you can notice कि जो भी आप फिजिबल, जो आप क्योंकि आप इंटरसेक्शन से निकाल रहे हो क्लोज्ड हाफ स्पेसेस, जो आपके कंस्ट्रेंट्स होते हैं वो हमेशा क्लोज्ड हाफ स्पेसेस बना रहे होते हैं. मैंने LPP, जनरल LPP is given to you. So when you take the intersection, so that becomes your polyhedral. That means जो हमने ग्राफिकल में किया था, जो मेरा फिजिबल रीजन बनता था, that is nothing but that is my polyhedral or polyhedron, right? So you say this is a polytope, you say polyhedral, if it is non-empty and bounded, अगर वो आपका, क्योंकि हमने किया था, जो हमने फिजिबल रीजन हम बनाते थे, हमारा कई बारी अनबाउंडेड रीजन भी बनता था, तो दैट मीन्स अगर आपका फिजिबल रीजन अनबाउंडेड बन रहा है तो वो पॉलीहेड्रल है, बट इट इज नॉट अ पॉलीटॉप, राइट। अगर आपका फिजिबल रीजन नॉन एम्प्टी है और बाउंडेड है, दैट इट इज बिकमिंग बाउंडेड, देन इट इज योर पॉलीटॉप। एंड वन इज लास्ट. Sometimes whenever we ask what is simplex, students say it is a method, but actually simplex method is a method. But what is simplex? A polytope having finite number of vertices. Having finite number of vertices. अगर आपके पॉलीटॉप के फाइनाइट वर्टिसेस हैं तब हम उसको बोलेंगे सिंप्लेक्स. Okay, hope this is clear to you. This is just the definition that you should remember, that what is your polyhedral. So whatever your feasible region becomes, अगर वो आपका unbounded है तो वो polytop नहीं है, but it is just a polyhedral. But if your feasible region is non-empty plus it is bounded, then you call it is a polytop. Simplex is if a polytop have finite number of vertices, then you say it is a simplex. Okay, thank you.